Let's look at a few examples of these sequences and whether they converge or not. So this is where we left off. We're going to go back and look at some more examples pertaining to these theorems and how to apply them. So going all the way back. Okay, so here's the first one. So the directions will be determine if the limit exists, and if so, find the limit. So in example number 1, the sequence 1 plus 1 over n to the n. And I went ahead and wrote this up just to speed things up a little bit. So we want to look at the limit of a sub n as n approaches infinity. Okay, so this is our limit. And so for something like this, we want to consider this as real numbers and what happens there. So if we look at oops, that didn't come out. So I was supposed to say let. So let f of x equal 1 plus 1 over x to the x. So do you recognize that function or not? We did that at the beginning of chapter 7, I believe. That function is e. So we showed that limit as x approaches infinity is equal to e. We're not going to go do that right now, but that's what we showed. So since the function for real values approaches e, so does the sequence. So that sequence approaches the number e. Okay, let's look at this one. We're going to use the Epsilon-delta proof to prove this one. So example number 2 is this you've seen many times. This is 1 over n. So we know that 1 over x basically approaches 0, right? So if you graph the function, you're getting this sort of thing. You know it goes like this, down like that, and it approaches 0. So we know it approaches 0, but let's prove it. Okay, so we're going to do this one using a proof. So prove that the limit of 1 over n as n approaches infinity is equal to 0. So we say proof, and then we're going to say let epsilon be greater than 0. So arbitrary value epsilon. Then we're going to do some research. I'm going to fix this a little bit. I can come over here. So my research, well, let me just show you. You can look at it later. It's not really research. I just want to get this out there so you see how this is done. So choose m. So let me go back to the definition. That's what I wanted to do. Sorry. That's the definition. No, that's not the definition. Sorry, that's a definition. So if there exists an n such that n greater than n implies the difference is always less than epsilon. So we gotta relate the L and the A sub n and the epsilon. So we're going to choose m. It doesn't matter the variable, but we're going to choose m to equal 1 over epsilon. Then, if n is greater than m, what we have then is absolute value of 1 over n minus 0 is equal to absolute value of 1 over n. But n is increasing, it's getting towards infinity, so we can just drop the opposite values. Just say 1 over n. That will be less than 1 over m because of this statement here. So if you have that and you divide both sides, you get 1 over m is greater than 1 over n, or 1 over n is less than 1 over m. So that's what I'm in say as an assertion because of this. But what did I choose m to be? I chose m to be 1 over epsilon. So that equals epsilon. So your choice of m greater than, or n greater than your m, implies that the difference is always less than epsilon. So if you're gonna, this is just an aside research stuff right here. Okay, so if anything's research, that's your research. Very well. Next example. Example 3. All right. So this time we have the sequence we have the sequence ln n squared. Be careful of your ln's and n's there. Over n. So this one's kind of strange. So when you see kind of like strange ones and it's not real clear, take a look at it in terms of real valued functions. So let's just let f of x equal ln x squared over x. Now we're going to find the limit of f of x as x approaches infinity. And keep in mind, we're always approaching infinity, right? You're not approaching a particular value. These are always going to infinity, and we're seeing what happens. So that's equal to the limit of ln x squared over x as x approaches infinity. So a direct substitution, you get infinity over infinity. So if you have infinity over infinity, what may you apply? Yes, you may apply L'Hopital's rule. So you take the derivative of the top, and you get basically 1 over x and then 2x. So it ends up reducing to, and you can check this. You could pause this and work through it actually at this point. Probably would have had you do that. So see if you can get this. So come back here and pause it and try it from there. That's still infinity over infinity, so you may apply L'Hopital's rule again. Factor out the 2, and you get 1 over x. Right, it's 1 over x times the derivative of what's inside. Derivative of the bottom is just 1, so that equals 0. So since f of x approaches 0 as x approaches infinity, the limit a sub n approaches 0 as x approaches infinity. Let's do example 4. Next sequence, a sub n equal to n minus 2 factorial over n factorial. And a little aside here, just in case you forgot, n factorial is defined to be n times n minus 1 times n minus 2, etc., 3, 2, 1. 0 factorial is defined to be 1. 1 factorial is defined to be 1 as well. So for example, if I said 5 factorial, then that is 5 times 4 times 3 times 2 times 1. The actual value doesn't really matter, frankly. One thing to note is that n factorial grows faster than e to the n, or so it's like this, is increasing. This is really increasing exponential, but this n factorial is like really fast increasing. Check out a few values. So plug in, so pick x to be, I don't know, 1,000. Check it out in your book. It's page 570. They give you some examples. So if n is, you can't do, that's too big. So if n is 20, e is almost 5 times 10 to the 8th. N factorial is 2.4 times 10 to the 18th. So this grows, factorials grow really fast. Just kind of a FYI. How you approach this is you simplify it. You apply the definition like this and simplify it. So we can take a sub n, the nth term, which is n minus 2 factorial over n factorial, and see how it is simplified. So this is n minus 2, and then it's n minus 2 minus 1, so it ends up being n minus 3, n minus 4 in that manner, and you continue to simplify that. So you say dot, 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 all the way down to 4 times 3 times 2 times 1, and that's all over n factorial. Well, n factorial is n times n minus 1 times n minus 2 times n minus 3. Can you see where this is going? All the way down to 4 times 2 times 3 times 1. So all of these terms, see how I don't want to do this. All of these terms, so let's see, all of these, let's change the size of that thing. So all of these and all of these reduce. They're gone. It's just 1. So that simplifies down to 1 over n times n minus 1. And so now take a limit, and you can see that that denominator, of course, this approaches infinity, and so the whole thing approaches 0. So we can say then that the limit of a sub n as n approaches infinity is equal to 0. So therefore converges. Probably need to be saying that in all these, huh? So converges, 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 etc. Let's take a look at a theorem. This is called the squeeze theorem or sandwich theorem. So squeeze theorem. I think your book says the sandwich theorem. It doesn't really matter. It says this. So if the limit of a sub n as n approaches infinity equals L, and the limit of b sub n as n approaches infinity equals L as well, and there exists a capital N such that a sub n is less than or equal to c sub n is less than or equal to b sub n. Eventually, so for all n greater than the capital N. So it's basically saying eventually you can show that C is always between A and B. And it doesn't matter if you pick A and B, but it's always sandwiched or squeezed between them eventually. So it may, I'm going to erase this, but it may jump. So this is what we showed in Calc 1 stuff, or single variable stuff. You have a function that does this and a function that does this. And then you have another function in between that you can say eventually goes like this. So it may go up and down, but between here and here, it's always true. Or actually, it would be like that. Then it converges to there. So it's sandwiched between those. Then the punchline, conclusion. What would you say? You'd say the limit of C sub n as n approaches infinity is equal to L. And let's look at an example of that. Suppose we have the sequence A sub n equal to sine n over n. So it's noted that sine of n is always between -1 and 1. Right, this is true. We know that. We know how sine oscillates, right? So sine oscillates like that. So we know that to be the case. So if you start off with a true statement like that, or something you know, then what we're going to do is divide by n. Now remember, n is always positive, so you have to worry about 0 or negatives at all. So you get 1 over n is less than or equal to sine n over n is less than or equal to 1 over n. Now remember, like I said, n is always positive and non-negative. It's always, it's not going to flip signs or anything or divide by 0, so you can just do that. But we know this, since the sequence plus or minus 1 over n always approaches 0 as n approaches infinity. So it's sandwiched, so both of these are going to 0, right? So this guy here, that one's going to 0, this one's going to 0. So therefore, by the sandwich theorem or squeeze theorem, sine n over n must also approach 0. And you can say that too. You can say by the squeeze theorem. Let's do another theorem. This is called, this is the absolute value theorem. This one states this: let A sub n be a sequence if the limit of the absolute value of A sub n as n approaches infinity equals 0, then basically taking off the absolute values also approaches 0. So then the limit of just A sub n as n approaches infinity is equal to 0. So if the absolute value approaches 0, we call that absolute convergence. So sometimes when they oscillate, they'll approach 0. Sometimes when you take their absolute values, it doesn't. But if the absolute value approaches 0, then we call that absolute convergence. Or converges absolutely is actually how they say it. Let's look at an example of that. So for example, let's find, so find or determine, right, the limit of -1 to the n plus 1 of 1 over n. And again, we're always approaching infinity. It's kind of a nice thing. So it's alternating, you know, it's, you want to, a lot of what you want to do here is, it is not just about finding the limit. It's showing the limit exists. It's showing what's occurring and stating why. So we're going to get more and more into that. So we can say, since the limit of the absolute value of -1 to the n plus 1 of 1 over n as n approaches infinity. So what happens there is that basically this is irrelevant because it doesn't change sign. So this will go directly to just 1 over n. So since that is equal to the limit as n approaches infinity of 1 over n, so we're saying they're equal, that equals 0. We actually proved by the definition that that equals 0. Then it converges. So therefore, the limit of a sub n as n approaches infinity is equal to 0, or converges. Okay, and that's by the theorem. All right, let's look at the bounded monotonic sequence concept. So if a sequence is bounded monotonic, then we know it converges. So this is just, I didn't really do an example of that. Let's look at this example. So a bounded monotonic sequence converges. So monotonic means it's non-increasing or non-decreasing. So it can be the same, but then it's either greater than or less than. So it can maybe slightly, be the same and then start increasing, or be the same and then start decreasing is the concept. So if we let's look at just the one we already know. We know that that converges and it converges to 0. But let's just investigate it just kind of directly without doing a limit or a limit definition. So we know this is bounded above by 1, right? Because you put in 1 is the smallest n, and it's 1. So we know it's bounded above. The largest value can be as 1. And we can also argue and bounded below by what? Like, what do you know it can't be, it can't get to, it can't be, it's always decreasing, so it's bounded below by 0. Okay. Also, we know it's monotonic. Okay, so it's monotonic, it's bounded above and bounded below, therefore it must converge. So it's monotonic, thus it converges. So that bounded monotonic sequence concepts, it doesn't tell you what it converges to, it just tells you that it exists. And sometimes that's good enough, because you can have computers, actually get a value that it's close to by running sequences. We know it can do that. But the concept is that you're not going to get like infinite loops and stuff like that if you're using computer concepts. Let's see. One more thing before we're done with this section. Just another theorem, because we're going to be using this a lot later. This one says r to the n, the limit of r to the n as n approaches infinity is equal to 0 if absolute value of r is less than 1. Okay, so kind of think about that one. And that the limit of the absolute value of r to the n as n approaches infinity is equal to infinity, or diverges, if the absolute value of r is greater than 1. Look at some of those proofs of that, or like kind of the argument at least. We can maybe talk about it later, but we're going to be using that concept for a number of things. So, for example, just quick investigations. If I have 4/3 to the n, or I have, well, let's talk about that one. So does that one converge or diverge? Well, you can see here that your r is greater than 1, therefore diverges. Okay, so that's because of this, right? You have your r here. You can look at absolute values, but that's not going to change anything. So it diverges. Let's look at this one. This one takes a little bit of work before you can finish it. So 2 to the n squared over 5n squared minus 3. So if we divide by n squared, we get 2 over 5 minus 3 over n squared. This may not have been a good example for that one above, but so that's, remember you did that in other forms. So this one here goes to 0, and so that's equal to 2/5. So if you do that, this approaches 2/5 as n approaches infinity. That wasn't actually a good example for that specific question. Just do one more. So if I flip that around and say 3/4, and actually, hey, how about let's do this? Let's make this another sequence. Let's do -1 to the n plus 1, and let's do 3/4 to the n. Does that converge or diverge? Well, if you look at the absolute value like this, then you're looking at the limit approaching infinity, and that ends up being just 3/4 to the n. Okay, well that's going to equal 0 because of this theorem here. So r is less than 1, right? 3/4 is less than 1. So because of that theorem, it's equal to 0. So the absolute value converges to 0. Therefore, the alternating case, we call this, I don't know if I mentioned that, that's called an alternating sequence. So if you have -1 to the n, that's called alternating sequence. So this converges absolutely then, because the absolute value of a sub n as n approaches infinity is equal to 0, which converges. So we can say, therefore, the sequence a sub n converges. And let's just say to 0 as well. Okay, and that's